Goddess of Science Physics, and I'm Mrs. Bolden. And today we're going to talk about the speed of sound. And that's part 4 of my sound series. Okay, let's get to it. So we got a couple of main ideas here. Whoa, section is so big it has 2 main ideas. The speed of sound in a gas depends upon the temperature of the gas and the mass of the particles in the gas. And the second main idea is the speed of sound in any material depends upon the material's elasticity. And we'll talk about what elasticity means a little bit later. Okay. So how do you know sound is slower than light? You probably have been in a thunderstorm at some point in your life, and you will see the lightning before you see the thunder. You hear the thunder because they happen at the same time, but because light travels like a quadrillion times faster than sound, you see the light before you hear the rumble of the thunder. So if you can try this out, without having a thunderstorm, if you see somebody hammering far away, you often see the blow and then you hear it. It takes time for the sound to reach your ears, but because what you're seeing is a light wave, that comes much, much faster. So you hear thunder after you see the lightning because the flash of light travels so much faster than the thunder. So the speed of sound in dry air at 0 degrees Celsius, which is 32 degrees Fahrenheit, is about 33 meters per second, which is 1/1,000,000th of the speed of light. So speed of light is 1,000,000 times greater than this. If you increase the temperature of the air, you also increase the speed of sound slightly. Faster moving particles will bump into each other more often. If the temperature is greater, that makes the molecules move around faster. That's why ice melts and you get liquid, because the molecules are moving around faster. If the temperature increases, the speed of sound is going to increase as well, because the faster the molecules are, the more chances they're going to bump into each other and transmit that disturbance faster. With each degree of increase in air temperature above 0 degrees Celsius, the speed of sound in the air is increased by 0.60 meters per second. So I feel like there might be some math involved here. If I give you a temperature, you should be able to calculate what the speed of sound is in that temperature. So at 0 is 330 meters per second. For every degree above that, you're going to increase it by 0.6 meters per second. Okay. So the speed of sound in a gas depends upon the mass of its particles. If you have helium, which has a very not helium, hydrogen, which is the lightest gas, the lighter particles like helium, which is He, and hydrogen, which is H, move faster and transmit sound faster than the heavier gases like oxygen and nitrogen. Air is really a mixture of all of those different gases. It's about 80% nitrogen and about 19-ish% oxygen. And then all the other gases that are in there are just less than 1% altogether. So anyway, the speed of sound in a solid depends upon the material's density and its elasticity. So what is this elasticity thing? It's the ability of a material to change shape in response to a force and then return to its initial shape. So if you take some silly putty and you squash it with your fist, it doesn't spring back and take its original form. But because it's a very inelastic substance, but things like metal will do that. With the tuning forks, if you strike the tuning fork, it will vibrate for a little while because it's coming back to its original shape. So that's elasticity. Steel is very elastic, and putty, clay, that kind of thing, very, very inelastic. So steel is going to conduct sound much faster than something inelastic like putty. Sound travels faster in very elastic materials. Okay, well, that's it for this time. Thanks for joining me. Have a great day.